All right, some of these slides can be kind of verbose, so I'll try and highlight the sections I think you should definitely write down. All right, so randomness is a very strange thing. And the idea of probability rests on this thing called the law of large numbers, where probability is only useful in the long run. So the law of large numbers says that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value, right? So the probably easiest one to think about is flipping a coin. And if I'm looking at the proportion of heads, the more I toss that coin, the more of the proportion of heads will stabilize, as long as it's a fair coin, near 0.5, right? And you can see that in the long run. Any short run, so you give me any finite number of coin flips, it's going to be impossible to predict the proportion of heads. Probability only stabilizes in the long run. What does the long run mean? That feels like maybe a little bit of a nebulous term. The long run means just continued repetitions. So infinite repetitions. So write down the law of large numbers, because that's what all of this, the rest of this unit is going to rest on. And then write down what's in green. The probability of the probability of any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. And it's important to understand that anytime you're asked to interpret a probability, you interpret it as a long run relative frequency. Remember what relative frequency is? Just number of proportions. It's the proportion of successes out of total outcomes. I'm going to give you just a quick example of that. I'll do it off in the corner over here. So like if I wanted to interpret the probability of heads being 0.5, the interpretation of that would be if I flipped a coin many times, I would expect the proportion of heads either to be about or to approach 0.5. All right, so here, many times, there's my long run relative frequency. And then remember, I would have to say to be about 0.5 or to approach 0.5, because anytime I flip the coin a finite number of times and stop, that's no longer long run. It could be a bunch of times, but now you have a finite number of times, so it's likely not going to be exactly what the theoretical probability is. It's going to be around that. Okay? All right, give me a green check if you're good with that. If you have questions about this, feel free to ask. So that's the law of large numbers, and that's probability. And we know we need to interpret it as a long run relative frequency. Here is how casinos make money. The myth of short run regularity. Random outcomes, randomness is predictable only in the long run. Remember what the long run is. It's continued trials. Continued, infinite, right? And sometimes our intuition tries to tell us that random phenomena should also be predictable in the short run. However, they're not. They're absolutely not. And then we get to the myth of the law of averages. There is no such thing as the law of averages. You see this in sports a lot, like in baseball. If, a good baseball player who has been historically good has a bad hitting streak, the announcers will sometimes be like, oh, he's due for a hit. And that's just not true, right? The universe doesn't need to balance out for some reason his hits, because you're only looking at it in the short run. You're looking at a finite number of trials. Also, the universe has no memory. Sometimes we call this the gambler's fallacy. And it's easiest to talk about. We're going to be talking about this game a lot. But do you guys know roulette? This is the one with the wheel and the black and red tiles. You put the marble in and you spin the wheel. And there's like a bunch of black and red tiles around the edge. And there's actually two green. There's a 0 and a double 0, and they're numbered. And you have the black tiles. And then so the marble spins around and it randomly falls into one of the tiles. And you can make a bunch of different bets on roulette. You can bet on the number you think that the ball is going to fall on. You can bet on if it's going to be even or odd. You can bet on if it's going to be black or red. Right? But what they will do, I think the simplest bet is the red-black bet, right? And the deal is there are 38 tiles. We'll go more into depth in this later when we talk about probability. But there are 18 black, 18 red, and 2 green. And so people like to make the red-black bet just because it's simple and you have a relatively high chance of winning. And basically, the payout on that is you would double your money. So if you bet $5 and you win, you get your money back plus an additional $5. But the probability of winning isn't above 50%. Of course not. That would lose the casino money. It's 18 out of 38, which is like 48% or something, 46%, something like that, right? But they'll also do this thing where they'll have this giant board, and it's a grid, and it basically will show what the last 50 spins were, okay? So it'll be like, it'll show the color and the number. So it'll be like, last one, the marble landed on black 36. One before that, it was, whatever, 15 red, and so on and so forth. That does not matter. That is only there. That board is only there to induce the gambler's fallacy because it's a short run. 50 spins doesn't mean anything, right? The universe has no memory of what the last spin was, but people will see like, uh-oh, the last 5 spins were black, so what should I bet on this time? Probably red. The universe wants to balance this out, right? It's got to be red if the last 5 spins were black. Not true at all. The table has no memory of what the last spin was. This is short run, and that sort of thinking is the gambler's fallacy. It's trying to think about the law of averages in the short run. There is no law of averages. There's only the law of large numbers. Now, that means this probability will only be true in the long run. Well, guess what? Any individual player is not playing in the long run. And even if you were, you would only win eventually 48% of the time, which means guess who wins the other 52% of the time? The casino. So they're the only ones making money because the casino is the only one continuously playing. They're playing in the long run. So they're going to reap the benefits of that 52%, right? They're guaranteed to do that, whereas you are not. All right. So that's the gambler's fallacy. So here were the steps to performing a simulation. All right, so we had state, plan, do, conclude. So state, what is the probability that you're looking for? Just make a statement about that and come up with a notation. So I'm going to make a little note there. Start getting used to using probability notation and labeling variables of interest. Like in the 1 in 6 wins, we decided to use X to represent the number of winners in one simulation of 7 people buying a soda, right? Plan, describe how you will use a chance device to imitate one repetition of the process. So make sure you understand what one simulation is. For us, we were using a die, but remember we were rolling it 7 times to represent one simulation in that last example. So you want to be very clear on how you are planning to simulate. So are you using a random number generator? If so, what's your labeling technique? Are repeats okay? Like in our last example, it was totally fine if we got multiple of any number, right? If we got multiple 6s, that just meant there were multiple wins. But sometimes repeats aren't okay, depending on the context of the situation. Do, perform many repetitions of the simulation. How many is many? Continued. Now we did 70, right? I think in the problems in your homework, it only asks you to do 10 because you're doing it by yourself. But just remember that the more simulations you did, the better approximation of the true probability you would get. And then conclude, make sure you answer your final question of interest that was stated in the state step. All right. Okay. I'm just going to walk you through a completed example. So you don't have to write down this example. We did one in the 1 in 6 wins. And then this one is just an example that's completed for you. And so you have these slides to read through. I'm just going to point out kind of all the important steps. And so it's a similar scenario to the one we did as an intro activity, but this one is just a different context. All right, so in an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of the NASCAR drivers, Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. The box of cereal says that each of the 5 cards is equally likely to appear in any box of cereal. A NASCAR fan decides to keep buying boxes of cereal until she has all 5 drivers' cards. She is surprised when it takes her 23 boxes to get a full set of cards. Should she be surprised? All right, so the problem is, what's the probability that it'll take 23 or more boxes to get a full set of 5 NASCAR collectible cards? All right, so this is state, basically. Right? The other thing I would do is I would describe a variable. I'm going to say let X be the number of boxes it takes to get a full set of cards, right? I should say, I'll be specific, of all 5 cards. And so really what I'm looking at is what's the probability that x is greater than or equal to 23, so that it takes 23 or more boxes, given that the probability of getting each card is 1 in 5, right? They're saying it's equally likely that any driver will be in each box. Okay. And so in this case, we're going to do it with a random number generator. So our plan is we're going to let 5 numbers represent the 5 possible cards, right? And so 1 is going to be Jeff Gordon, 2, Dale Earnhardt Jr., 3, Tony Stewart, 4, Danica Patrick, and 5, Jimmy Johnson. And then we can use our calculator to generate a random number from 1 to 5. And every time we generate a random number, that represents buying 1 box of cereal. And all we want to do is just keep pressing enter until we've covered all 5 numbers, right? So you're probably going to get some repeats. But once you get all 5 numbers, you'll record the number of boxes, which we called X, that we had to open until we got all 5 numbers from 1 to 5. Does that make sense? And so one simulation is once you get all 5 boxes. So in this case, each simulation will probably have a different number of plays, right? What's the minimum number it could take you? What's the minimum value of X? Good, 5. And the maximum value is not defined, right? It could potentially take you infinitely many times. Now, it becomes increasingly unlikely like the further you go up, right? All right, so that's our plan. Okay, so here's a simulation. We did 50 simulations, and here's an example of each one of these is a different simulation. So here's an example of 5 simulations, right? In one, it took 9 boxes, in one 16, in one 10, in one 15, and in one 22. And so we did that a total of 50 times. I made this dot plot. And so if I want to know the probability that 23 or more is roughly 0. We didn't have any out of our 50 simulations that took 23 or more. The most it took was 22 boxes, right? So in this case, what would we conclude? We would conclude that she probably should be surprised about how many boxes she had to buy. Now, I don't know what recourse she has. I guess she could hire a lawyer, and the lawyer could audit the company. But yes, she should probably be surprised because it's extremely unlikely, based on our simulation, that if each box is equally likely that it would take 23 or more boxes. Does that make sense? All right, and so that's it. There's just another example of a complete simulation.